So imagine you're playing a tower defense game, but instead of, building turrets to shoot at a swarm of incoming enemies, you just physically tilt the game board so they all roll harmlessly away. Today, we are taking a deep dive into the Geodesic Sheild proposal by 206 Innovation Inc.
Right, and our mission today is really to figure out how taking that exact concept, like bending an environment rather than fighting in it, might completely revolutionize modern defense.
It's because it completely abandons what we normally think of as Newtonian physics, right?
Exactly. Traditional defense is all about force-based kinetic intercepts, a missile hitting a drone. But this software treats the operational environment as a dynamic curvature field.
A dynamic curvature field.
Yeah, it passively deflects and contains threats just by mathematically altering the space they move through.
Okay, I need to wrap my head around that. How exactly does a purely mathematical software program actually tilt the board? Like, what is doing the bending here?
Well, it starts with the geometry of the system. The software builds an icosahedral lattice. So think of it like an invisible 3D geometric grid mapped over an area. And it contains exactly 642 intersection points, or nodes.
Okay, so 642 nodes.
Right. And this grid uses a mathematical tool called the Dillon operator. You can picture the Dillon operator as this highly sensitive digital level. It constantly measures the flatness of the space.
Oh, so it's looking for any changes in that flatness.
Precisely. When an incoming threat enters, its mass and velocity create a bump, or what they call gradient stress, in that data. The system detects that bump and actively flattens it out.
Wow.
Yeah, and in phase I testing, doing this actively dropped threat penetration probabilities from a highly vulnerable 68% down to just 24%.
That is a massive drop. But I am struggling to picture this in the real world. If a physical drone swarm is flying in at 100 miles an hour and this math smooths out the terrain, where does all that kinetic energy actually go?
That is the big question.
Right, because it can't just vanish into a spreadsheet. Doesn't it just act like an invisible digital brick wall? Like, wouldn't it cause the drones to bounce off chaotically and create all sorts of collateral damage?
No, and that is actually the genius of it. It isn't a wall at all. The lattice acts more like a geometric shock absorber.
A shock absorber?
Yeah, when that drone swarm hits the stabilized zone, the system mathematically dissipates the swarm's kinetic energy across the various edges of that 3D grid we talked about.
Oh, so it spreads the impact out.
Exactly. It drains the threat's momentum by continuously smoothing out the curvature of the field around it, rather than trying to, smash the drones to pieces with an opposing physical force.
But for the military to actually trust a system that alters the geometry of a battlefield, it can't just work most of the time. It has to be 100% predictable.
Oh, absolutely.
And from the sources we're looking at, it sounds like they have essentially built a DVR for reality. Like, if you rewind an attack scenario and hit play, the exact same pixel-perfect event happens every single time. How is that even possible?
Well, it is completely different from standard military war games. If you've ever looked at standard simulations, you know they use Monte Carlo randomness.
Right, where you run them thousands of times, rolling digital dice to get an aggregate probability of what might happen.
Exactly. But the Geodesic Sheild doesn't do that. It enforces strict, hard determinism using a hardware component they call the L5 overlay processor.
And what does that L5 processor actually do to stop the digital dice from rolling?
It runs cryptographic checksums every single time step. Basically, it mathematically verifies that the state of the grid is exactly as it should be, down to the decimal every 41 milliseconds.
Every 41 milliseconds? That is incredibly fast.
It is. And because there is no random chance involved, it achieves absolute zero divergence on replay. So you get lightning fast, perfect predictability.
But before this perfect digital DVR can be deployed to protect real infrastructure, it faces a pretty massive hurdle, right? Like what they call the calibration gap?
Yeah, the calibration gap is the real test here.
Because right now, this is incredibly elegant, abstract math, but eventually that math has to anchor to messy, real-world physical environments for you to actually use it.
Precisely. They have to prove that a mathematical bump in the data actually maps to a physical threat in reality, which is why there is a live demonstration scheduled for 2026 in Yellowstone National Park.
Yellowstone? Why there?
Well, they are going to take live geological and seismic data, like the immense physical pressure of a geyser about to erupt, and dynamically update the simulation.
Oh.
Yeah, they want to see if physical real-world pressure can be instantly translated into the digital gradient stress we talked about earlier.
And if they pull that off, their roadmap goes way beyond just physical defense. The architects of this system have a plan ending in 2033 called the Jubilee.
The Jubilee, yeah.
where they actually want to apply this exact deterministic math to sociology.
Which is a massive leap. I mean, obviously. It is
Mhm.
one thing to mathematically dissipate the kinetic energy of a drone swarm across a physical grid.
Right.
But it is entirely another to apply those same geometric constraints to model macro-societal dynamics in human behavior.
It really is, which leaves you with this to ponder. If an algorithm can successfully bend the physical trajectory of a missile to avoid a strike, could it eventually map and bend the trajectory of macro-human conflict toward reconciliation? Like, could we literally just tilt the board of global warfare so the conflict rolls harmlessly away?